Hi, 11. Today we start a new chapter, which is chapter 20 on vectors. Today we'll look in this session at 20a, which is Introduction to Vectors. For the whole chapter, those are the all the objectives that will be broken down into different exercises. Um, So if you want to have a read through all of those, you can pause this first slide. Moving on with introduction to vectors. With this video, what we're looking at is first is defining what a vector is. So a vector is a set of equivalent directed line segments. So line defined as being a straight link segment, it will have a start and a finish. So um, before I move on to this one, so the visual representation a vector, you have that segment from A to B, that arrow with that annotation. We could also use a different one. That is a visual representation of a vector. It will link back to a Cartesian plane and coordinates, but here you have additional information. Not only you have the length from A to B, but as well you will have the direction from A to B. So A is the start, B is the finish, and the arrow indicates the direction. Once we have defined those, we have a few rules. The first one is addition of vectors. So once to define it, so we define two vectors. Here the addition is we have um, u plus v. So starting from A, you go to B, then to C. It's also equal from A to C. So what, to summarize, is um, all you care is the starting and the ending point. The path is irrelevant. So you can break down any vector AC as a sum of two different vectors, and we'll look at it into details a little bit later. Um, and then we'll link back to further down the road to a subtraction. Before I do the subtraction, we do a scalar multiplication. So a scalar is you multiply a vector or any amount with a real number, which is a scalar amount. Now, when that number is in a particular situation, when that number is equal to -1, that's how we can define the opposite vector. So when you have u equals ab, you multiply by -1, it's negative ab, which is you basically swapping the start and finish, and the notation is ba with the arrow on top. This is the common notation you would use in your workbook. Um, the textbook will tend to use the bold font to annotate a vector, which is easier in terms of writing print notation. Zero vector is a vector that has a no direction and a zero length. Is basically the start and end will be the same point. Once we've done going back to the multiplying by -1, that will link further down to the subtraction. When you have u minus v, when you want to subtract two vectors, it's the same as adding the opposite vector. So you write graphically, you will have u and v. To do the subtraction, you will do the representation of negative v. And what you do is graphically you will shift it down to meet the end of vector u, and as you follow the path in blue, we have the subtraction of the two vectors. Last one, which is quite important as well, is when you have two parallel vectors, they are linked algebraically as the formula or an equation is the other vector can be expressed as a scalar product and be equal to the first one. We'll see that a little bit more into details, and examples 4 and 5 will be tasks for you to apply in terms of proofing and using the notation and the relation of parallel vectors. So let's go through a few examples, starting with the visual representation and the notation. So example 1 is draw a directed line segment corresponding to 3 and -2. Now, differently from Cartesian plane and coordinates, when you had those Cartesian coordinates, you will usually start from the origin. With vectors, the starting point can be any point in space. So on your Cartesian plane, when you draw that vector, if I start with a random point A, which has the coordinates 1, 1, to draw that vector, you will go 3 across and 2 downwards, and here is a representation of those vector coordinates. If you were to start from anywhere, you can have an equivalent vector of that representation as long as it will be parallel, but also you will have the same um, displacement to the right and downwards. All right. Next one. Vector u is defined by the direct line segment from those 2 points. If you want to attempt that, you should pause the video right now. Let me continue. So you have u is equal to that. When you do is you can do a representation by placing the coordinates here and there. Another way to do it algebraically is this is your starting point and that's your end point. A better representation to do this is this point will represent A and that is B. As you go from A to B is u is equal to vector AB. Okay, and what we'll see later is we can represent vector AB as a sum of vectors and also a difference, and this is an important notation that you should be using quite commonly when you want to introduce the origin. And vector OB represents the coordinate of point B, and vector OA represents the coordinate of A. Notice there's a minus because we have to use the opposite vector of OA. And to summarize here, you go over here. I'm just giving you a better explanation how they get to the difference here. So then they will respectively do the difference of the x and y coordinates, simplify, and you will have the vector u expressed over here. So again, what it means is 1 across to the right and 5 units downwards. It will link back to the rise of a run in your Pythagorean representation and also in terms of gradient. Example 3 relates to the sum, could be the difference, but also a scalar multiplication. So you have those 2 vectors in terms of Cartesian coordinates. You notice you multiply by scalar 2 and 3 respectively. If you want to attempt that, just pause the video. And let's continue. So multiply 2 and 3 respectively, you combine it, and as you add it, you add respectively the x and y coordinates, and you end up with the sum of the two vectors. So algebraically, it should be pretty straightforward. All right, let's move on to a little bit different concept this time. It's a little bit more to do with the geometrical representation. When you had two vectors AB and BC, so AB plus BC is the same to AC. So you have the same starting point and the same end point, and those can be represented as in a vector sum. Now, if you have a polygon, so you go from A and you go all the way around, following the vertices all the way back to the starting point. So the start point and end point are the same. As you add them all up, it will simplify to a vector, a null vector, or AA, because you have the same start and end point. Notice the points are in common here. And you go back to the null, simplify to a null vector. So with example 4, illustrate the vector sum. So you have three vectors, you need to add them all up together. So what you draw is your vector, a random vector AB, BC starts from B, you continue, and CD, and then the sum of those three vectors is summarized down below. You go straight from A to D. Okay. Just a reminder also for this section, with any representation, just use a ruler as well, which is a good practice. All right, before we move on to the last two examples, few properties that are going to be really useful in terms of vector proofing is when two vectors u and v are parallel, we can summarize that as a algebraic relationship or formula. Okay, and k is a coefficient that it might be given to you or you must determine. Okay, and that can be positive or negative, fractional, or any real value. Okay, down below is when you have a linear combination of non-parallel vector. So you have a vector that is equal to that sum on the left hand side, and to be equal to the right hand side, the coefficients need to be matching. So m has to be equal to p, and n has to be equal to q. If you think about it in the Cartesian plane representation, when you have a point A that has specific coordinates and to be placed on the Cartesian plane, so for example 2 and 3, those values 2 and 3 will be unique. So whatever you have here, 2 and 3 over there, whatever you have that vector equal, it will need to be the same values for any combination you need to come up with. All right, so example, you have a situation, you have a triangle, you have your drawing with ABC. It tells you that D is the midpoint of BC, so it's in the middle. And we define, just to simplify, because later we have to express all those combination of vectors, and to simplify the notation, we define vector A and vector B to be AB and BC here. A good idea to annotate those vector A and B over here, so I would do something like that. Okay, and then you will have to express B, all those vectors in terms of A and B. So have a go at this, pause the video, and then we'll continue. All right, let's continue. So with this, um, the idea here for the first one is using the parallel vectors property. So being in the mid, D being the middle, BD is half of BC. It's just a visual representation. We'll see later on how to do that algebraically. And what it means, it's half of vector B. DC is the second half, so we can do the same here. Okay. Now, with AC, we just uh, separate that into a sum of two vectors, vector AB and vector BC, and we just substitute. Okay. You do the same with D. The last bit is using the opposite vector to change the order of the start and finish. And as it is the opposite of AC, AC has been solved in part C, and we can just write with the negative coefficient. And don't forget the bracket, as it is a common factor. All right. With the last one, you might need, again, attempt this one, pause the video. You might need to spend a little bit more time. It is a typical question you will find on the SAC, also on the exam, and also in the Year 12 exams, if you continue with specialists, when you have questions that will involve proofing with vectors. All right, so pause this one and attempt as much as you can. All right, let's continue. First one, part A, is critical that you get the first part A right. So you're going to be able to continue later on. Now, K is your unknown. You'll find out in part C that you need to find the value of it. So let's continue with the solution. So to express P in terms of all of those coefficients, so you need to you should have annotated that P is over here. You have your vector Q um, over here and R. So P is AB, and you need to define a path. So you go from A, D, C, B, and you can write your expression over here. All right, and you that is equation. You can rearrange it to make P the subject. All right. Now we move on to part B. So FE is over here. So what we do is we use a path to go all the way to A, to B, and back to E. We can write this expression over here. Okay. And now from part A, we can rewrite simplify the expression. So that factor is over here. We can substitute with this bit. So we can write that expression. We expand the bracket and simplify. We have the final expression of FE. And then for the last bit, because we know we have FE equals 4AB, we just substitute from part B, and that gives us an equation. And again, it's going back to, just let me go back to a previous slide. It's the linear combination of non-parallel vectors. So you have an expression on the left is equal to an expression on the right, it implies the coefficients need to be equal. So here we have an expression in terms of P and in terms of P, and it means that the coefficient on the left needs to match the coefficient on the right. We make it equal and we solve for K. And that's it for this session. See you later.